All right, so we're ready to talk about the hyperbola, which is kind of similar in feel to the ellipse, but definitely looks completely different. So look at that. The official definition of a hyperbola is just that it's the set of points such that the differences of the distances from each point to two fixed points, which are the foci, is constant. So if you recall from the ellipse, we had a center, which the hyperbola still has a center. We had two foci, F1 and F2, and we would have a point that was on our curve. And if you looked at the distance between the point and one focus and the point and the other focus in the ellipse, when you added them together, it was constant no matter where that point was. Well, in a hyperbola, when you subtract them, now that's the constant. So if you take this distance and subtract that distance, you'll always get the same value no matter where point P is along the curve. And we actually call the curve branches of our hyperbola. And there's two branches, and you'll see they either open up like this, or they can open up and down. Let's see, what else? The branches themselves kind of look like parabolas, which they are not, so don't get those confused, but they do have vertices just like a parabola does. And so if you look at these 2 points, these are the vertices, and the distance from the center to each vertex is the length of A. So 2A is going to be the length of PF1 minus PF2. Kind of like that whole major axis thing from the ellipse. Okay, moving on. So let's take a look at the equations. Here are the equations. Yes, there are two different equations for the equation of a hyperbola, and that is because you are subtracting. And you know there's a difference when you subtract which number is subtracted from the other. You're going to get a different answer. So one hyperbola is where the x squared comes first, and then you're subtracting the y squared. The other hyperbola is when the y squared comes first, and then you're subtracting the x squared. Notice both of these have an h and k. That's going to be your vertex. They both have a squared and b squared in the denominators. And it just really tells you exactly the same thing in the ellipse, how far you're moving away from the center in the x and y direction. So here's one version of the hyperbola. This is the hyperbola when the x squared comes first. Notice that the branches are opening in the x direction. That's going to be really important. Hyperbolas have asymptotes, as you see here in purple. These blue points, those are the vertices. And you might be wondering what this box is. And that box isn't anything officially a part of the hyperbola. It's just something useful. It's a useful tool to figure out where your asymptotes are to help you figure out where the branches are. These yellow points right here, I forgot to label them, but these are your focal points. So this is F1, this is F2. Notice that they are within the curve of each of these branches. They are not within the box, but within the curve. So you move beyond the vertice to get to the foci. Okay, you see something very similar over here. The only difference is that the branches are opening in the y direction. They're opening up and down. You still have asymptotes, you still have this funny box, you still have vertices, and your foci are within the curve of your branches. So if you look, the y came first. That means your branches are opening in the y direction. Over here, x came first, so the branches open in the x direction. Now we do have a formula to calculate out this distance from the center to each focal point, and it looks very similar to what we did with the ellipse, and that is c squared is equal to a squared plus b squared. If you recall in the ellipse, this formula was c squared equal to a squared minus b squared. So it's just the difference of a sign. So a neat way to remember which one goes with what, in the equation of the hyperbola, you're subtracting. For the foci, you're adding. And if you recall in the ellipse, the equation of the ellipse you were adding, and then this equation you were subtracting. So it's just opposite for each of them. Okay, so let's get to our first example. We have x squared over 25 minus y squared over 9 is equal to 1. The first step should always be to figure out what your center is. In this case, it's pretty easy because the center is the origin. So I'm going to go ahead and plot that. Okay. Next thing is we want to figure out what a and b are. So take the square root of both of these numbers. We have 5 and 3. So the 5 being under the x means we're going to move 5 units in the x direction away from the center. So 1, 2, 3, 4, 5. 5, there we go. And then the 3 in the y, 1, 2, 3, 1, 2, 3. Okay, so far this feels very similar to what we did in the ellipse. Had this been a plus sign here, we would be done. We would just connect the dots and get our ellipse. But it's not, it's a minus sign, that means it's a hyperbola. So what we're going to do here is we're going to make our box. All right, now technically our box should be dashed, but I don't have that ability with this tool, so it's going to be solid. And so what you're going to do to make your box is these 4 points are going to be on the edges or on the sides, so you know exactly the dimensions. Okay, so now what we're going to do is make our asymptotes. I will make them purple. We'll make lines. And if you recall, the asymptotes should be dashed as well. And it's not actually going to be dashed because once again I can't make that on this tool. Okay, so they do go from vertex to vertex of your rectangle, which is why we made it. So basically they are the diagonals of your rectangle elongated. Okay, so remember all of this should be dashed, right? Good. All right, so that's the setup. We are now ready to figure out where to draw in our branches. So if you recall, you're going to be looking at which variable comes first, right? Which one's positive. So since x squared is positive, our branches are going to open up in the x direction. So now this is going to be really funny to watch. I will do the best I can. You always start at this point. Since it's in the x direction, we're going to start at this point. If it were in the y direction, we'd start at that point. These are the vertices, right? Oh, that was bad. Okay, so I'm going to draw towards my asymptote here. Ooh, don't laugh. Okay, so there's one branch, and then you go and you do it on the other side. Sorry this is taking so long, but you get the idea. You guys will be all over it. Okay, so the key is to make sure that your asymptotes are drawn long enough past these corners so that you have something to draw your branches towards. Sorry. Okay, so next, what can we do with this? Well, they are going to ask for the equations of the asymptotes. Well, asymptotes are just lines, right? So y equals mx plus b. So both of these purple lines pass through the origin, so the y-intercept here is going to be the origin, which is 0. So that means we are just concentrating on y equals mx. Well, what's the slope? Well, you can easily read that off going from this point up to that point. Just count it. You're going up 3 and over 5, rise over run. Or if you're doing this asymptote, you're going up 3 and to the left 5. So that's how we get our two equations of our asymptotes. Now if you think about it, these numbers 3 and 5, they came from this number and that number, rise over run, 3 over 5. So you could do that, you could calculate it out without actually graphing it. Okay, the next thing they're going to ask you to do is to actually calculate out where the foci are and what the coordinates are. So remember our formula, c squared equals a squared plus b squared, so 25 plus 9. We get 34, so c is going to be plus or minus the square root of 34. Now, if you recall, foci are going to be within the branches of your hyperbola. So let's make them yellow. And I'm just going to pick a random place here and here. Okay, that's just to help me figure out, what direction I'm moving, where I'm supposed to go. Not that that's an accurate representation of where those points are. But I do know I'm going to go for my center, and I'm going to add the square root of 34 to get to this point, and I'm going to go for my center and subtract the square root of 34 to get to this point. So the y-coordinate is still 0, it's the x-coordinate that's changing. So here are the coordinates of your asymptote, or of your foci. God, I keep getting that mixed up. Okay, sorry this has taken so long, but these are long problems. We have one more example that I want to do, which is a little bit more complicated. So let's take a look at that one. Okay, so you can see why this one's more complicated. The center is not at the origin. And even better, y is coming first. So this is tricky. You need to make sure that you get the coordinates correct, the x-coordinate and the y-coordinate for your for your center. You cannot just go in order left, right. So the center in this one is going to be -2, +1. Okay, very clear. So let's go ahead and plot that. -2, +1. Okay. So the next thing is to figure out where our vertices are. And remember, our vertices are going to come from finding those points on our box. So let's actually do that. Here's the 2 squared and the 4 squared. So let's see, moving 2 in the y direction, 1, 2, and 4 in the x direction, 1, 2, 4. Okay, and let's actually go ahead and make our box. Remember, boxes should be dashed as well. They're not really part of the graph. Okay. Yeah, let's go ahead and draw in our asymptotes while we're at it, shall we? Let's see, we'll change this to purple line. Here we go. And the next one. Okay. So the vertices, we're going to get those by figuring out what direction our hyperbola's branches are going to open. And because the y is coming first, the branches are going to open in the y direction. So that means that this point right here and that point right there are going to end up being your vertices. So you can either just read off the coordinates, which it looks like we're going -2 and up 1, 2, 3, and -2 and down 1. Notice that it has the same x-coordinate of our center, and we're adding, we're adding 2 to the y-coordinate and subtracting 2 from the y-coordinate. So you can actually do this calculation without graphing, just understanding what your graph is going to look like, and getting that number and adding and subtracting it from the y-coordinate of your center. Okay, so why don't we just go ahead and draw in our branches while we're here. Might as well finish it off, yeah. Whoops, whoa, that was bad. Should not go beyond the asymptote there, but I can't help it with this computer mouse. Okay, ooh, that was a close one. All right. Not my best, but you get the idea. All right, next thing, we need to figure out our foci. So in order to figure out our foci, we need to do our equation. C squared equals a squared plus b squared. So we get the square root of 20, which is 2 root 5, plus or minus. Once again, just as a reference, I'm going to put my foci here and here so that I have something to reference. Looks like I'm going to be going from my center, and I'm going to be adding 2 root 5 and subtracting 2 root 5 from the y-coordinate. So start here and just take the 1 and add and subtract 2 root 5. Seems fairly simple enough, yeah? Okay. Last thing is we need to do the equations of the asymptotes. Well, once again, equation of a line, y equals mx plus b. Unfortunately, you can see they both have different y-intercepts. So you could do it, but it's a little bit messier. Instead, why don't we take this point that they both have in common and use that and the slope in our point-slope form? Okay, well, this point that they both have in common is the center. And you can easily read off the slope, rise over run, or look at the 2 over the 4, simplified as 1/2. So remember, y minus y1 equals m times x minus x1. Plug in your y1 and x1, which is your I don't know why this says vertex, that should say center. Cross that off. Hello. Center. Okay. So plugging in x1 and y1 for your center, and then figuring out your slope and just plugging that in, you're done. One's positive, one's negative. And if you notice, the y minus 1 and the x plus 2, well, that came from here and here. It's identical from the equation. So that makes it really easy. Okay, so that's it. That's hyperbolas. I know that's a lot of information. These problems take a while to do, but essentially they're not that bad. Okay, good luck, folks.